I'm going live on YouTube now. Going live on YouTube now. Okay. So I think that we are ready to go. Going live on YouTube now. All right. So welcome, guys. Welcome. I see that there are quite a few of you here on time and ready to delve into the electrolysis calculations that we said that we'd be doing and focusing on exclusively this week. And so I'll pick up, we'll just kind of do a quick recap of what we did last time, and then we'll jump into the calculations. And then I also wanted to speak to you guys about the marathon past paper, like the actual CXC past paper marathon sessions that I have planned for April. See if you guys would be interested in terms of like time and you know, whatever the rate I've came up with, just telling you guys about that as well. But I want to wait a little bit until the others are here. But in the meantime, I'll go ahead and get started with the lesson for today / the calculation problem solving session. Okay, how does that sound to you guys? Let me know.
Sounds good, miss.
Okay, so electrolysis calculations is where we are. So let me just start from this slide. But what I want to do, let me do share my screen. This is it. So click from current slides. So electrolysis calculations is what we're focusing on for today, right? But before I jump into it, I kind of want somebody to give me just a quick recap or a quick overview of what we did last time, so we can just move forward. So just, I guess what I kind of want to hear from somebody, anybody who's brave enough to take the stand and let me know what is electrolysis in your own words, like how would you define it, and who are the key players in electrolysis? So we have electrolytes, we have electrodes, and we have the different kinds of electrodes and different kinds of reactions happen there. So essentially what I want one person to tell me, and then somebody else can talk to us about the electrochemical series. How about that? Anybody brave enough to just give us an overview of electrolysis on a whole? And then somebody can tell us about the electrochemical series and how that whole thing comes into play. Let's see, I'm waiting on you. I'm waiting on somebody to step up and let me know what's going on with this whole electrolysis thing. So we're all on the same page, moving forward with the calculations for today. That's my rationale, okay? That's why I'm asking you. It's not to stress you guys out, but it's to just make sure that you're understanding and are on the same page. Maybe you rewatched the class from last time and you got a new perspective on things. So let me know where you guys are. Are you guys hearing me? Let me see if I can put this up here. Okay, so it's up there now. Okay, Elizabeth, I'm gonna call on you because I see that you're highlighted. So I'm assuming that you want to say something to me. Jabari says electrolysis is the transfer of electrons through an electrolyte. Yes, that's exactly right. So it's the movement of those charged species through an electrolyte, right? And then really that results in a chemical change. Remember, we always have to get that lysis part in our definition, where we have like a chemical change or a decomposition or a breaking up, if you would, of those of that electrolyte, right? So it's not just a transfer, but that transfer occurs and that results in a chemical change or a decomposition of your electrolyte species, right? So that's exactly right. So thank you so much for that, Jabari. And I was saying that Elizabeth is highlighted, so it seems as though you want to share with us, Elizabeth, or no? I don't hear her. It looks like she walked away or something. Okay. So maybe I should do this. Let's do this. Let me go back. Let me go back and just do a quick high-level overview. How do you guys feel about that? Are you all up to speed on everything and are ready to jump into calculations? Or you want me to just go back to that slide where I have all the elements and do a quick overview? Okay, I see Claude is saying something. Claude says that the cathode is the positive electrodes which attracts cations. Let's think about that. The cathode attracts cations, right? Cations are positive. So that means that the cathode is the negative electrode. So the cathode is a negative electrode. It attracts the positive species or the positive ions that are known as cations. So because the cations are attracted to it, then that means that it's negative because positive attracts to negative. And in the anode now, the anode, anions are attracted to the anode, and that's because the anode is positively charged. So you have a positively charged anode that attracts our negatively charged anions, right? Okay, so is that clear to you for you now, Claude? I'm gonna go over that. I'm gonna go back to that one slide that kind of encapsulates everything, and then we'll move forward from there because I want everybody to be on the same page. Because like, if I jump into the calculation and somebody doesn't really know what the different species are, then it will be tricky. You know, it won't make sense. So let me just go over that real quick. I'm gonna go on this slide. Let me pick this slide. And let me fix this so that this, okay. So I'm gonna share my screen again. Just like this. Okay. Why did it? All right, I guess that didn't quite work. But anyways, okay. All right, guys. So this is the slide, right? Very loud on this with all these colors. So electrolysis is the decomposition of a compound by an electric current. So essentially what Jabari was getting at, right? We have an electric current and we're passing it through what we call an electrolyte, which in this case is our molten NaCl. And we're passing an electric current through this molten NaCl, which has these charged species in it, these charged ions that can then move around, right? On the application of that electric current, right? So this electrolyte gets decomposed by that electric current, right? That's the compound in question here, right? So we have, if we take this example again, we have sodium chloride, that's our electrolyte. That molten sodium chloride is made up of sodium ion, which is our cation, and chloride ion, which is our anion, right? As we said before, we have these things called electrodes. These are regions in our electrochemical cell or in our electrolytic cell. These are kind of like poles, right, to which the species move, right? So the cathode, as we said, goes along with the first part of this thing called cation. It's a cation, this positively charged thing. So cations go to the cathode, and cations are positively charged ions, and they go towards the cathode because the cathode, this whole thing is negatively charged, right? So opposites attract. Your cation is attracted to the cathode, which is negative. If we're all on the same page there, give me a thumbs up. So cations go to the cathode because the cathode is negative, right? All right, so I see some thumbs up there. So just to make sure we're clear on that, right? Then we have our anode. The first part of this word an comes from anion, which means that the anions go towards the anode. And the reason why is because the anions are negatively charged. They want to go somewhere positive, and the anode is positively charged. All right, is that making sense? This is very important stuff going forward. So let me know if that makes sense. Now I see those thumbs up. Okay, so that makes sense. So we have our electrodes, we have our anode, we have our cathode. We mentioned earlier how we have two classes of electrodes. We have inert and we have active. Can somebody give me two examples of inert electrodes? Like what would make up, what element or what chemical, what compounds would make up an inert electrode versus our very common active electrode? Can somebody give me an example of what you'd be looking out for if I say inert versus active?
Repeat, miss.
What's the most common example of an active electrode that you will encounter that we didn't encounter last week and we spoke about it, right? The most common example of an active electrode that you will encounter in this class. Let me see in the chat. Kayla said copper is the common one, and that's exactly right. Jabari says platinum is inert, copper is active. That's great. All right, so we're on the same page there. And when we say it's active, we mean that it can actually take part in the electrolysis reaction, and it can actually maybe whatever the species are or is that makes up that electrode will actually be preferentially discharged compared to whatever is in that electrolyte, right? So these are things that we have to look out for. And so then that whole idea then of having an active electrode and how that then can compete with your ions in the solution brings us to this idea of an electrochemical series. So let me just skip to this real quick so we can see this, right? And the electrochemical series is telling us the tendency of ions to discharge, right? So whether it's a cation or anion, as you go down, right, the tendency to discharge increases as you go further and further down this column, right? Same thing here, same thing here. So essentially, if you have an electrolyte solution and it has chlorine and hydroxide in it, hydroxide is the one that's going to get preferentially discharged, right? And we said anions go towards the anode. So let me just grab my pen real quick because it's another point I want to make on this side and then we move on. But anions go towards the anode and then cations go towards the cathode, as we said, right? So I said the further down it is, if you're choosing between this and this, because the hydroxide is further down, this is the one that would win, and this is the one that would, something would happen to it at the anode, right? What would happen to it? Like what kind of reaction did we say happen at the anode? It's a class of reactions that typically take place at the anode, right? And the anode is where the anion is. So let's use chlorine, for example, but OH, in this particular case, OH would be preferentially discharged. But for the intents and purposes of the reaction that I'm talking about with you guys now, let's use chlorine, the chloride ion, right? We have our chloride ion, it's getting discharged at the anode. What's gonna happen to it from a reaction standpoint? and what's then the final state of it gonna be. So essentially what we're getting into now is the reactions that take place and the half equations that we're gonna then have to write to be able to do the electrolysis calculation. So let me know. I see something in the chat. Jamar says that oxidation takes place at the anode. Okay, Jamar, do you want to expound on that a little bit for us? That's exactly right. That's correct. But I want you to expound on it a little bit. So help me with this half equation, what this half equation would look like for the chloride ion, if it is that it is indeed oxidized at the anode, right? You said oxidation takes place at the anode. Walk me through what would happen to this chloride ion at the anode.
Miss, it's 2 chloride ions yield Cl2 plus electrons.
So let me write that real quick. So you're saying, that this is supposed to be 2 chloride ion, and then what you said happened now?
Miss yield Cl2 plus 2E minus.
And then the state of this is what? Gas? And then
Yes,
what's the state of this?
Miss aqueous, miss.
Okay. All right. So you're saying that this is an oxidation process. Is that what you said?
Yes, miss.
So you're saying oxidation takes place at the anode, and oxidation is
That's the loss of electrons.
so that's oil, right? Oxidation is a loss of electrons. So over here, we have our chloride ion, and it's an anion. And the reason why it became an anion, it became negatively charged, is because it had gained electrons, right? So now the balance between the electrons and the protons was off, and you had more electrons than you had protons. And so that's why you end up with a net negative charge, right? So that's why you have your Cl minus on the left here, right? So now if we're saying oxidation is loss, what's happening then is that chloride ion is then gonna lose those 2 electrons, right? And when it loses those 2 electrons, then it's gonna end up in its neutral state, which is then Cl2 gas. And so you have oxidation that takes place then, right? Because you're going from a negative charge here. Let me get back my mouse. You're going from a negative charge on the left to on chlorine on the right, it's 0. So you see that you're going from -1 to 0. So there's an increase in the oxidation number, which means that oxidation takes place. Okay? So as a general rule, oxidation takes place at the anode. Oxidation takes place at the anode, right? Oxidation is a loss of electrons. So whatever species is at the anode is gonna get oxidized, right? Is that clear? Okay, cool. And then cathode now, at the cathode, what takes place at the cathode? Somebody else tell me what takes place at the cathode, and just kind of explain it to me how I just explained it for the anode in terms of like electron loss and how cations are formed and how they're then going to become neutral as a result of what happens. Who can explain that to me? Anybody? Jamar, did you want to go again? I see that you're highlighted.
Miss reduction hammer at the cathode, miss.
Okay, and then tell me how it work out now.
Miss where electrons are gained. So like when the cation would gain an electron to become stable, to become neutral.
Become neutral, yeah. Okay, and so it's going from a state where it had lost an electron because it was that's how it became positive in the first place, right? So it became Na. It went from sodium. The sodium was neutral first, right? Something happened for it to become Na plus, and that something that happened was that it lost its outermost electron. So now what's happening is it wants to gain that back. So it wants to be reduced, and it's going to be reduced at the cathode. So reduction takes place there, and then now it's going to become neutral sodium again. Remember that? Okay, I see thumbs up. So I think that this is like sharp and crystal clear in your guys' head. So I'm gonna move on to the electrolysis calculations now, right? Is that okay with you guys? Okay. Elizabeth, your hand is raised. You can go ahead and talk to me.
No, Miss, you can go ahead and move on. Sorry.
Oh, okay. Because I saw that your hand was raised.
Yeah, sorry about that, Miss.
Okay, are you guys seeing that? Right, electrolysis calculations now, right? And so essentially, what we're talking about is the transfer of charges, right? That takes place in electrolysis, right? You have your species that's getting, in the case of the anode, it's getting what? What takes place at the anode? It's getting oxidized at the anode, right? So there's a transfer of electrons that's taking place. At the cathode, you have reduction. So it's a transfer of electrons that's taking place, and that's a charge transfer, right? So no, I mean, when we talk about charged particles can be ions or electrons. So just, I just wanted to clarify that. There's a transfer of these charged particles that takes place during electrolysis, really, which is why it gets the name electrolysis, right? So the first definition here that I have for you guys is electric charge. And that electric charge is very important because, as we said, they're charged species, electronically charged pieces that are being transferred. And so if we're going to be able to do calculations, we have to know how we can actually apply, put a metric, put a number on these charged species. And so we speak about an electric charge, which the unit is in coulombs, and that gets transferred throughout the electrolytic cell. And so the electric charge transferred is given by Q is equal to I times T, right? And Q is the charge, the electric charge. I is the current that you're passing through that electrolytic cell. And time, T, is the amount of time for which you're allowing that current to flow, right? So you can flow the current for 5 seconds, you can flow it for 20 seconds, you can flow it for a day, however long. There's a time associated with that, and there's a current in amperes associated with that. And then when you multiply those two things, you get a charge, an electric charge that's gonna then flow through that cell, okay? So then now we speak about the Faraday's constant, which is very important in this section. Its symbol is F. And what the Faraday constant is, it's the quantity of electric charge. So that's Q. How much Q is carried by what? Guys, pay attention to this stuff in purple. 1 mole of electrons or 1 mole of singly charged ions. Singly charged ions. This is very important. That's how we find the Faraday constant. It's in terms of a mole of electrons or a mole of singly charged ions. Now you'll see later on that the reason why it's important to distinguish this is because there are doubly charged ions and there are triply charged ions as well. So we have to know what exactly the species is in question that we're talking about. And since we're here talking about doubly charged, singly charged, let me just show you what I mean by that. We'll get into it later, but let me show you now while I have this opportunity. When we talk about singly charged, we'd probably speak about a magnesium, a sodium kind of thing, where it's like just +1, right? Doubly charged would be magnesium, right? Triply charged would be aluminum. So just keep these things in mind, right? Just keep this in mind. And what we're saying is that the quantity of electric charge carried by 1 mole, so if we're carrying 1 mole of electrons, which would be in the case of sodium, where we need to at that it's at the cathode because the cation, right? For reduction, it would need to gain back that 1 mole of electron that it lost. So then for that to take place, we would need 96,500 coulombs per mole, right? So that's a 1 mole of single charge, right? If it's a doubly charged thing like magnesium, we would need 2 times that amount because the basis is for 1 mole of singly charged ions, right? So just keep that in mind. Does that make sense to you guys, or is that confusing? Doubly charged versus singly charged versus triply charged. You have to be comfortable with that, okay? Okay. Very good. I see some thumbs up, so I think it's clear. Not as many as I'd like. So if there are any questions on that, please let me know before I jump to the next slide. Okay. Okay, so we just established this Faraday constant thing. It's the quantity of electric charge that's carried by 1 mole of electrons or 1 mole of singly charged ions, right? Its approximate value is 96,500 coulombs per mole. So it's the amount of charge that's carried per mole, right? So just keep that in mind. This is a very important number for you to commit to memory so you can easily remember that, right? That's Faraday's constant. All right. Now we have 2 laws, right? That govern this whole electrolysis calculation stuff. The first law is Faraday's first law, and that just states that the mass liberated during electrolysis is directly proportional to the amount of electricity, which is our I, right, or electric current, which has passed through the cell, right? So the mass that gets liberated is directly proportional to the amount of electricity which has passed through the cell. So the amount of electricity, if we go back, would be, well, if we speak of an amount like an overall amount, and we measure that as the overall electric charge, then that amount would be Q is equal to I times T, and the electric current itself is I, but when you multiply that by how long it has been flowed for through the cell, then you get the charge, which is your overall electricity then that's going through that cell. So what they're saying here, Faraday's first law is saying that the mass of stuff that you're gonna get, whether that's by oxidation or reduction, is directly proportional to the amount of electricity which has passed through the cell. So what that means is, because it says directly proportional, directly means that if this increase, they're like directly related. If one thing happens to this, the same thing happens to the other. So what that looks like then, if you have a large amount of electricity that you're flowing through the cell, then you're gonna get a large mass of stuff that gets liberated. Okay? Does that make sense? That's that direct proportionality. That's what that means. If it's directly proportional to the electricity, the more electricity, the more mass, right? More electricity, more mass. The less electricity, less mass of stuff. Okay? Let me know if that's clear. And then now we jump to the second law. Is the first law clear to you guys? Okay. Okay. I see Kaylee's thumbs up. Okay. So the second law, this way of saying is a little bit trickier. So I'm going to read it and I'm going to give you a smaller, a shorter way of saying it. Let me see if we're saying something in the chat. Okay, Akila says yes, ma'am. Okay. When the same amount of electricity is passed through a number of electrolytes in series, the masses of the products liberated are in the ratio of their equivalent weight. Let's not focus on this one too much. But this is just saying that if you have electrolytes and you have like one here, and you have another one, and they're like in series like this, the masses of the products that get liberated, like as you go in that series, that the mass is, they're in a ratio of their equivalent weight, right? So they're in series, same current passing through. So whatever mass you're gonna get is then equivalent to the ratio of their equivalent weight. It's a little bit tricky. You would have to just see an example to get that, to make that a little bit clearer. But an alternate,
Could you re-explain, please?
I probably have to show you an example to make it clear, but let me just kind of show you from a sketching standpoint what we mean. So we have electrolytes in series, right? So in this series, it's like one after the other, one after the other. It's a physics concept, like the way that they're talking about it when they say series versus parallel, right? You probably are aware with that, of that from physics. So if there's series, they're like one after the other, right? So like I just do those three things right there, 3 sticks, right? One of those, each of those sticks represent an electrolyte, right? So if you have those electrolytes in series, which means that they're one after the other, the same amount of electricity is passed through them, right? Whatever passed through, let me get my pen. Yeah, whatever passed through 1 passes through 2, and it also then passes through 3, right? So they're saying now that the masses of their products are in the ratio of their equivalent weight. So like so the mass of this is X, and the mass of this is Y, and then the mass of this is Z. Then the ratio, the mass of the products that gets liberated, which is X, Y, Z, are in the ratio of their equivalent weight. So X to Y to Z would be equivalent to whatever the weight of X is. So how would I frame it? Let me frame it like this. So say the, what would I say? Let me use AR values. So AR of X to AR of Y to AR. So the AR is what the relative atomic mass, right? So like that's just essentially what this is saying in simpler terms. But what I want you guys to take away from this, which is the alternate way how I'm gonna say it, is very important and has implications for when you have not singly charged species. You have doubly charged species and you have triply charged species, right? So I'm gonna share a whiteboard and write this out on it. The alternate phrasing of the second law, which I definitely want you guys to pay attention to, because this is more, you can see it more clearly what it means when I say it like this. I'm trying to get my whiteboard so I can write this on it. Let's see. All right, so I'm gonna stop sharing this now. So stop share. And then I'm gonna, did that help, Kalia? Did that help a little bit?
Yes, miss.
Okay, so I'm gonna write this in a text box. So this is an alternate phrase of the second law, and it says that the number of Faradays required to discharge. So already you see a new word, Faradays. I didn't tell you about Faradays before. I told you about Faraday's constant. I didn't tell you about Faradays per se, right? But this alternate phrasing of the second law says that the number of Faradays required to discharge one mole of an ion at an electrode is equal to the size of the charge on the ion. So I think this is a little bit more conceptually very much easier to grasp than what I had just now. And so the number of Faradays, right, is what we just said. So let me write this F in lowercase. So the number of Faradays required to discharge 1 mole of an ion at an electrode is equal to the size of the charge on the ion. So what that means is then, right, that 1 Faraday, can somebody tell me what this means? So 1 Faraday would then do what? 1 Faraday would be required to discharge 1 mole of an ion with a single charge. And this was I mentioned, I alluded to this earlier when I was saying that when we talk about a single charge, we can talk about sodium. Very often we'll talk about sodium chloride solutions, whether that's a molten solution or an aqueous solution. And so that's Na plus, right? You would need 2 Faradays. We just say Faradays. If we're doing, say, Cu for copper, right? So like Cu2 plus, because copper is 2 plus, right? That's a charge on it typically. When it's in that ionic state or when it's in that, so copper 2 sulfate is typically the electrolyte solution that we'll be looking at. So 2 Faradays will be needed for that. And then as I mentioned earlier, when I was talking about the 3 triplet charge, I said aluminum is our example because aluminum is in group 3. It has 3 valence electrons that it typically loses. And so 3 Faradays will be needed to discharge Al3 plus. All right. You guys get that now? Is that clear? The number
Yes.
of Faradays is what you need to discharge 1 mole of an ion at an electrode, and that is equal to the size of the charge on the ion. So that's what that looks like. And then generally, how you would get the number of Faradays, you see? This is important too as we move forward, right? So we can actually calculate the number of Faradays. Number of Faradays is equal to the quantity of charge that you get. Like when you do a calculation, when you do that, Q is equal to I times T, you get your quantity of charge. So that's your Q, right? So let me just do that. I times T, that's what we said earlier, divided by, so I guess I should divide here as well, divided by Faraday's constant, which is that number that I introduced you guys to earlier. That's where we started to get this definition from about Faraday's constant is the amount of electricity charge when you have 1 mole of electrons or 1 mole of single charge ions, right? So because we know as chemists, having studied this thing extensively, we know that we don't always have a single charge species. Sometimes we have doubly charged, sometimes we have triply charged. And so we have to be able to account for those when we do electrolysis. And so that's where this definition of a Faraday comes in very handy, right? So the number of Faradays is calculated by the quantity of charge Q divided by Faraday's constant. So I'm just breaking it down further. So then it would be, number of Faradays would be equal to I times T, because that's Q, divided by 96,500, because that's Faraday's constant, right? And the units of this is, the units of the Faraday's constant is what? What again, guys? Coulomb per mole, right? Yes, so that's the unit of the Faraday's constant. This just the bottom piece, right? And then the units of the top part would be what, guys? You know I'm big on units because units tell you a lot about what's going on. The units of this top part would be what, guys? That's a charge. So the units would be what? Coulombs, right? Units is coulomb. So essentially then what we're doing is what? What are we dividing by what now? We're dividing coulombs by coulombs per mole, right? So in the end, what does that give us? Because this is very important. I'm happy that we're like going over this. It gives you moles, right? So you're gonna do, let me just make it clear to everybody.
Coulombs are cancel coulombs, miss. Right?
Exactly. So coulomb divided by coulomb per mole. So the coulombs cancel and that mole comes up top, right? All right, so then let me just write that. Units of, or I don't want to say units of Faradays per se, but like when you get Faradays, it's equivalent to moles. Faradays is equivalent to moles of yeah, so let's just say it like that. And as we go through some examples, it will become more clear and clear to you guys how these Faraday's thing come into play, okay? So is this clear so far? Because now we're gonna jump into the meat of the matter, right? But I just want to make sure this is all clear with you guys. Is it clear? I'm looking for your thumbs up, you know. That's how I'm interacting with you. So I'm looking for thumbs up to see if that's clear, and then we just jump to the next thing, which is the calculations. Okay, so I see those thumbs up. I see all those thumbs up. So let me clear this now. Did you guys jot this down, or how do you? I mean, I'm not sure how you guys approach this, if you're taking notes or what. But do you have this already? Okay, all right, so I'm gonna clear it then, okay? Clear that, and then I'm gonna stop sharing that and then go back to my presentation. So, yes, all right, so now we're ready. We are ready to do calculations, right? So this one is really emphasizing the first law. So Faraday's first law, again, we said, can somebody remind me what it is? The first law is relating the quantity of charge to the mass that gets deposited, right? And what did we say? The amount of mass that gets deposited is dependent on the quantity of charge, right? The electric charge that flows through that cell. So the more electric charge you have flowing through, is the greater the amount of mass that's going to get produced, right? And so for this particular example calculation, we are electrolyzing molten sodium chloride, right? So that's NaCl. So we're doing NaCl, which is in its molten state. And so we're electrolyzing this. That's our electrolyte. And the time that they gave us is that the electricity is being flowed for 32 minutes and 10 seconds. So can somebody put this whole thing in seconds for me? Because that's the units that we're working with, is seconds. We can't have any 32 minutes, 10 second situation going on. It has to be all in seconds. So tell me what that time is in seconds. And then our I they gave us is 5 amperes. So we have I and T, and that's typically where we're starting from, because really and truly, the first thing that you should always write down when you see a problem like this is really the governing equation, the equation that's going to govern everything and govern all these calculations. And that's this: Q is equal to I times T, right? But I immediately jumped to being like, okay, they're saying they're saying t is equal to 32 minutes and 10 seconds, and then this is our I. So now we have to multiply. So like that's why I wrote these down first. So just make sure that we're all on the same page. Q is equal to IT. So we're finding the mass of chlorine, right? And the first thing that we said was the relationship between the mass and the electric charge is that the mass is directly proportional to the electric charge. So how do we go and find our electric charge? Let's do that first. Q is equal to I times T. They gave us that I is equal to 5 amperes and that the time is 32 minutes and 10 seconds. What is that in that whole thing in seconds? 32 minutes is how many seconds? And then just add that to your 10 seconds. So how many seconds is that? I don't know where this is. How many seconds is that? 1,930 is what people are saying in the chat. So that's 1,930 seconds, right? Oof. Okay, so I just brought up the calculation. So let's just work with that. All right, so it's 5 amperes times 1,930 seconds. So that's 9,650 coulombs, right? Are we all on the same page as far as that goes? All right, so that's 9,650 coulombs. That's our Q. That's the amount of electric charge that's flowing through our electrolytic cell, right? So then our next step then is to find the equivalent Faradays, because then that can clue us into how many, what mole of electrons is being moved, really, right? So Aquila is pointing down. She's giving me a thumbs down. So can you come and hop on your microphone and let me know what's missing here for you?
We saw them get the 1,930.
So it's just converting the 32 minutes and 10 seconds into the whole thing into seconds. So if you put 32 minutes to second, that would be what? 1 minute is 60 seconds, so 32 times 60 plus 10. Does that make sense?
Oh, yeah. Yes, miss.
Okay, okay. All right, so we found the number. So we have our Q. Q is equal to I times T. And just now I said, okay, if we want to find the number of Faradays, then we do the Q divided by Faraday's constant. So we did that. And so we have 0.1 Faradays, right? So the 0.1 Faradays means that, what does that mean? 0.1 Faradays means that we have, it's 0.1 moles of electrons that's getting discharged, right? And because we know that for chlorine is a single charge, negatively charged species, then we know that that's the amount of moles of electrons that getting discharged. So let me just write out that. The next step, guys, is to write your half equation. That's where we are. Right? So let's write our half equation. Can somebody write a half equation corresponding to this for me? What's the half equation for the electrolysis of sodium chloride, particularly where it is that the chlorine would get discharged? I mean, so somebody can answer this and maybe write the half equation too, right? Because in this case, they didn't give us a half equation, so we have to come up with it ourselves. Anybody? Anybody wants to tell me this half equation? Right, I'm gonna write it because you guys aren't volunteering. So let me do it. Okay, I think, can I draw now? Yeah, so Jamar is saying what is in the chat. Guys, if you want, if I'm like writing on the screen or I'm like trying to write on the screen and you have something to say, you can just unmute and say it, okay? Just unmute and say what you're saying. You don't always have to write in the chat. You can say it out loud. You can unmute and say it, okay? So we can all hear and then, yeah. I'm trying to get this thing to write on, I don't know why it's not working. Okay. All right. So if you have anything to say while I'm writing, just shout it out. So, because I'm not going to be looking at the chat, okay? So the chlorine now, the half equation is generally this. It's normally written as this. So let me write that. Let me change the color to, I want to write it in green. I'm going to write in a darker green. So 2Cl minus yields your Cl2 gas, and that's what they're asking us. This is actually what they want us to find, is the mass of this. How much of this is going to get produced given these specific parameters, right? Right, are we all happy with this half equation? Okay, and we see that we're going from -1 to 0. So it's an increase in oxidation number. So it's oxidation that takes place. So this is at the anode actually, right? That this is taking place. So this is at our anode. Brittany says she doesn't understand the half equation. So that half equation came from what we mentioned earlier, where we were saying that anodes go towards the anion, sorry, goes towards the anode, right? And the anions are negatively charged. And essentially, because of the anode oxidation takes place, what's going to happen is you have this anion here. It wants to become neutral again. And in this neutral state, it's Cl2, right? And so because it wants to become neutral and over here is negatively charged, to get back to that neutral state, it then has to, what has to happen to those electrons that it gained? It has to lose them, right? So oxidation takes place, it loses those two, it ends up being 2 electrons because you have to balance the charge, right? Over here, so it ends up being 2 electrons because you have 2 negative charges. So it ends up being 2 electrons that it then loses to enter this neutral state again. An alternate way of writing it is also like this. If it's easier for you to see what's happening this way, you can write like this. You can just say 2Cl minus is losing those 2 electrons to then become Cl2 gas, right? So that's an alternate way of writing it. Maybe it's easier for you to see it that way, but essentially what we're saying is that this is at our anode, the anode portion of the cell, and at the anode, oxidation takes place, and oxidation is loss of electrons. So that's oil, right? Remember that mnemonic? Oil rig. So oxidation is lost because this chlorine, in order to become negative, what had happened was it had gained an extra electron, and because of that, it became negatively charged. Now it wants to go back to be neutral at that anode. And so because it wants to go back to be neutral, because it had gained that electron, it had to now lose it. It has to now give it up. And that loss is what we call oxidation. And we can write that as is shown here, where we have our 2Cl minus losing those 2 electrons, right, to go to that neutral chlorine diatomic gas. Because chlorine is a diatomic gas, that's how we really ended up with that 2 before the chloride ion, and that's how we ended up with those 2 electrons being lost, okay? Is that clear before I add on anything else and confuse you further? Is that clear so far? Brittany, I was asking a question. So like, if you're answering, please unmute yourself and answer. Because I can't check the chat right now, okay? So if you're answering, if it's clear or not clear, just unmute yourself and let me know, because I can't check the chat.
Here, miss.
Okay, so that's how we got that half equation, right? So this is where it gets fun now. Now we get to crunch the numbers and do the calculation, which is what I've been like boosting you guys up to do this whole session, is to be able to now do this calculation with all this in the background, right? This background knowledge. All right. So we calculated our Faradays first. And so, okay, this is where mole concept comes in and stoichiometric ratios, right? We are saying that if we look at what we're essentially looking at, guys, when we're doing these electrolysis calculations, is we're looking at the number of moles of charged species that get transferred. So the number of moles of electrons that get transferred, and then as a result of that, the mass of stuff that we get. Because it's the amount of electrons that get transferred that gives us the quantity or the overall charge that gets moved throughout the system. And then as a result of that, that tells us how much mass of stuff will be deposited or produced, whether it's at the anode or at the cathode. So the importance of the half equation, where the half equation comes in this whole thing, is us saying, oh, we were able, from Q is equal to IT, we were able to calculate our number of Faradays. That's 0.1 Faradays. And that 0.1 Faradays is telling us that, okay, we have this general stoichiometric equation that we just wrote. So the general balanced equation that's of what's happening at the anode, which is this, or the top one, whichever one makes more sense to you. But let's just look at this equation, right? We have this equation. This equation is telling us, right, that 2 moles of electrons, 2 moles of E, right? This is from here, is what gets transferred in the general stoichiometric equation to give you then 1 mole of chlorine, right? Are you guys following that? If you're not following, let me know. 1 mole of Cl2. So we're going back to mole concept now. This equation, because I said stoichiometric equations are moles is the language. If you see a number before any number, that's a mole. So 2 moles of electrons is what's giving us that 1 mole of chlorine molecule. That's what this means. So the important part of the equation then for you, when you're doing electrolysis calculations, once you've written your half equation, what you're then gonna do is really home in on the number of electrons, the moles of electrons, and what stoichiometric ratio that is in with your desired product that you're finding the mass of. Most often is what you're finding, because that's what the first law is really speaking about, the relationship between the charge and the mass that you then get from that charge, right? So the balanced stoichiometric equation, that half equation, is telling us that for every 2 moles of electrons that you transfer, you get 1 mole of chlorine molecule, right? All right. The Q is equal to IT tells us how many moles of stuff was passed through, aka how many Faradays, right? So the number of Faradays we said was 0.1 Faradays, which is essentially moles, the amount of moles. Remember I showed that unit thing when I was showing you how the coulomb divided by coulomb per mole ends up being mole, and that's your Faraday? All right. Does everybody remember that? When I showed you how the coulomb divided by the coulomb per mole is moles, which is essentially a Faraday? You remember that? If you remember it, let me know. Okay, so then now what that means then is that, okay, the stoichiometric equation told us that we have 2 moles of electrons being transferred to give us that 1 mole of chlorine molecule. The Faraday, that number that we calculated that's right below that equation in blue, is telling us that we have, that because of the quantity of electricity that we're transferring, we're actually, in this particular case, we're only moving 0.1 moles of electrons. Does everybody follow that analysis? Because that number of Faradays that we calculated was from the amount of the Q that they gave us and the time. So the current and the time, right? So at a basic level, under normal circumstances, we would get 2 moles of electrons giving us a mole of chlorine molecule, right? But we don't have 2 moles of electrons because the current that we're flowing is not going to be able to move 2 moles. Instead, it's going to be able to move only 0.1 moles of electrons. And so going back to your mole concept knowledge that we worked very hard on during these 3 sessions, based on this balance equation, the stoichiometric ratio that I just wrote in blue here, right? If we are only moving 0.1 moles of electrons through this system, how many moles of chlorine molecule are we then going to be able to make? If everything was in our favor and we had 2 moles, we'd get 1 mole of chlorine molecule, but we don't have 2 moles. Now we only have 0.1 moles. That's that 0.1 Faradays, essentially. So if we only have 0.1 moles of electrons that we can move, that means that we're going to get 0.1 divided by 2 moles of chlorine molecule. So how much is that? That's 0.05, right? That's 0.05 moles of Cl2. Does everybody follow that? I'm not writing it because my thing is stuck again. I can't find my pencil again.
Yes, it said 0.05 or 0.5.
0.05. Because it's 0.1 divided by 2, right?
Okay.
So let me write it. I really don't like when my thing sticks. So that's why I said you guys should just talk out so I don't have to check the chat every minute and switch up my pointer. So let me see if I can write here. Okay, so here we are now. So we said 0.1 moles. That's what we got when we did our Q calculation. It told us that we only have 0.1 moles of electrons. And that then, based on our mole concept knowledge and our usage of ratios, we see that we're only then going to be able to get from that half the amount because a 2 to 1, right? So we're going to get 0.05 moles of Cl. And how much is that in mass? Can anyone tell me? We did that a lot. We spent a lot of time on this in our mole concept sessions as well. It's transitioning from moles to mass. So we know the moles of chlorine molecule that we have now, and the question asks us to find the mass of chlorine that we produce. So what's our mass? And then we're done with this.
That's 1.775 gram.
What was that?
1.775 gram.
1.775 gram is what you got.
Yes, for some reason I have 0.025.
Wait, let me think about this. 1 mole. Let me think about this. So wait, what did you get, Aquila? Is that you who said you got what? What were you saying that you got?
0.025.
0.025. All right, let's think about this. 2 moles would give you 1 mole. 9,650. So that would be 0.1 Faraday. 1 Faraday is required to remove 1 mole. 0.1 Faraday is gonna produce 2 moles gives us 1 mole, so that's half the amount. One Faraday, 2 Faradays. Oh yeah, so 2 Faradays would give us 1 mole. Okay, yeah. Okay, let's think about it that way. So let's back up a little bit here. Let's think of so we're consistent with what we're comparing. Let's think of the 2 moles in terms of Faradays, so that we're not messing up the units here, because what happened is, so 2 moles of electrons from the general equation, right, from the balance equation, 2 moles of electron will give us 1 mole of chlorine, right? 1 mole, let's bring it down to a 1 molar basis, because that's what we define the Faraday's constant and the Faraday in terms of. So let me just like back up a little bit here to make sure that we're on the same page. But essentially what we're doing is just a mole concept analysis right now. So well, let's just make sure that we get the definitions clearly, so that, let me erase this real quick. Let me erase the last bit that we did with the mole concept analysis. Where's my eraser? So essentially what I'm trying to what I'm clarifying here to allow you guys to see what the actual answer is. I'm gonna just write up top because I can't seem to erase that. So all right, so 2 moles, right? I'm gonna rewrite it again. So follow me up top here again in this pink writing. So 2 moles of electrons from our balanced equation, right, is gonna give us 2 moles of Cl. Two, right? So then now 1 mole of ease of electrons is gonna get us 0.5, right, moles of Cl2, right? Are we on the same page there? So it's 2 to 1, 1 to a half, right? So then essentially what this is saying is, if we go back to our Faraday's constant, it's saying that 1 Faraday, right, this bottom line, because when we remember the definition of Faraday's constant, it's saying that it's the quantity of electron, the quantity of electric charge that would be required to move 1 mole of electrons. That was the basis of our definition, right? So this is essentially the second line that I wrote, is essentially saying that 1 Faraday, right? Are you guys following with that jump that I just made? 1 Faraday gives us 0.5 moles of Cl2. Because remember that we said from the Faraday's constant is the electric charge required to move a mole of singly charged ion in an electrolytic cell. So that's equivalent to what 1 Faraday is, and that's what we got. That's what this stoichiometric ratio is saying here. And all of this is this first part. These first 2 lines that I wrote up here in pink are coming from just the stoichiometric equation. 2 moles of electrons give you 1 mole of chlorine molecule. 1 mole of electrons is going to give you 0.5 moles of chlorine molecule. And we know that 1 mole of electrons is the same as saying 1 Faraday is going to give you 0.5 moles of chlorine molecule, right? So if we know that 1 Faraday is going to give us 0.5 moles of chlorine molecule, and we know that we have 0.1 Faraday, right? Going back down to that blue at bottom, let me get my mouse so I can move it down and show you.
Miss, one question. Sorry.
Go ahead.
What you stated up there, you have 0.5, isn't it 0.05?
So it's 0.5 in that case because we're going from a molar basis as a comparison. Does that make sense? Before I was jumping ahead. I was jumping ahead to the 0.1 molar basis, but let's not do that. Let's do the molar basis because that's how we define the Faraday's constant. Does that make sense?
Okay.
So that's what I'm clarifying now to make sure we're all on the same page with that. So let me just, if I can, let me just erase this so I don't confuse you guys with down here. But essentially what I'm saying is let's stick to using a molar basis so we're all on the same page because the number that, somebody gave me a number and somebody gave me another number. And that's because I think there's like a disconnect in terms of what the basis is that we're using. So what I'm saying is let's use a molar basis, and that molar basis is coming from the definition of Faraday's constant as well as just mole concept in general. So the 2 to 1, the 2 moles of electrons to 1 mole of chlorine molecule is coming from this equation. That's your mole equation, your basic mole equation. And that's the same. We can also write that as 1 mole of electrons goes to 0.5 moles of chlorine molecule because it's 2 to 1, right? So you're always going to have twice as much. If you have however many moles of electrons that you're moving, you're only going to be able to convert that to half a mole of that molecule. Does that make sense? Of the corresponding molecule. And in this case, it's the chlorine molecule. So going back to Faraday's constant and that definition, 1 Faraday then is equivalent to that 1 mole of electrons. And so that would give us 0.5 moles of Cl2. So these two things are interchangeable now, right? Remember I said you can interchange the Faraday and the mole. Wait, what happened? Okay. So like this. So these two things are interchangeable. So that's why these two things say the same thing. 1 mole of electrons goes to 0.5 moles of chlorine molecule. And so 1 Faraday is the same as saying 1 Faraday is going to give us 0.5 moles of chlorine, right? Are we on the same page there? Let me know if you're confused or if this is clearer or what, because now we're going to move on to the next step, which is then to say, we determined that we have 0.1 Faradays, right? Because what I just wrote up top is a general basic thing that based on what we know about Faraday's constant and what we know about our chlorine, that's the general basic pattern or stoichiometric ratio that it should follow. But as we said earlier, we only have 0.1 Faradays. 1 Faraday is going to give us 0.5 moles of chlorine molecule, but we only have 0.1 Faradays. So how many moles then of chlorine are we going to get from that? Let's start there. And then once you get that mole, you convert that to mass, and that's your answer. So anybody wants to take that and run with it for me? 1 Faraday gives us 0.5 moles. We got it from our stoichiometric equation, from our half equation, right? But we don't have 1 Faraday. We have 0.1 Faraday. So how many moles of chlorine molecule is 0.1 Faraday gonna give us? That's where we are. Okay, are we all on the same page there? Or is there any confusion? Please feel free to unmute your mic and ask me so we can clarify, but that's where we are now. How about that?
Excuse me, miss.
Okay, go ahead.
Miss, so since they're interchangeable, we could work with the 2 mole equal to 1, then we could have find like 0.1 equal to x. Or is the second line necessary?
I think the second line is necessary because how do I put this? How do I explain this? Or is there a step that's missing there? So I think let's work with the second line. We can do it both ways, you know. We could actually do it both ways and see that it's not gonna work out to be exactly the same, because just now, all right, let's finish this. Finish this and see the answer that you get, and then we'll see if you would have gotten the same answer the other way. How about that? Because the molar basis is important in terms of defining what the Faraday would look like. Because if you do a 2 molar basis, right, here's the thing. Who asked that question? I couldn't see. Was it Claude?
No, Jabari.
Jabari, okay. So here's the thing, Jabari. Because this is where it gets tricky. Because the definition of Faraday's constant is in terms of 1 mole of singly charged ions, is if we just jump from the 2 moles, right, to 0.1 moles, and then just kind of use a correlation like that, I think what would happen is we wouldn't be accounting for the fact that this is a singly charged species. We would probably be doubling up on our answer, if that makes sense. So if you bring it down to the molar basis and just correlate that 1 mole to that 1 Faraday, by doing that, you're taking into account the fact that this is a mole of singly charged species. Does that make sense? Like, so when you say a mole of electrons, and then you can say, oh, that mole is equivalent to 1 Faraday, you're saying that this is for a mole of singly charged ions, as opposed to a mole of doubly charged or a mole of anything else, because then that will kind of throw it off. And I have some examples, some other questions that we can do for singly charged or doubly charged species. But for the singly charged species, at the basic level, right, the correlation is between, or the definition of the Faraday's constant is for singly charged species, right? And because that's what we're using when we're doing the calculation for the Faradays and everything, if we're gonna say 1 mole of electrons being moved is equivalent to 1 Faraday, right, for that singly charged species, then it's best if we just say, oh, let's go from mole of electron to 1 Faraday. And then we can say, oh, 0.1 Faraday gives us X moles of chlorine molecule. Does that make sense? I think it'll be easier to see if I show you contrasting examples, then you can see it. But if we just continue on with this problem, let's see what answer we get, right?
Okay.
Does anybody have an answer?
This will be 0.05.
So it's 0. Wait, go ahead.
This will be 0.5 times 0.1, which will give 0.05 chlorine, moles of chlorine.
Okay, that's exactly right. So 0.0, let me write that. Let me write that. Okay, so let me just write that real quick. And then we have to talk about our next step. So let me just bring it down here. So 1 Faraday goes to 0.5 moles of Cl2, and we only have 0.1, right? So from that 0.1, we can only get X moles, and that X is equal to 0.1 times 0.5, which is 0.05 moles of Cl2, and 0.05 moles of Cl2 is what in mass?
Mr. says 0.5 what, miss? Repeat, please.
0.05 moles of Cl2 is how many mass? What's the mass of that?
It's 3.5.
How much is it?
Should be 3.5 grams.
3 point. Oh, it sounds like you're rounding off early, so.
Miss, the molar mass of chlorine is 35, miss.
871. Because remember, it's diatomy?
No, as in 35 times 2, miss. I was saying that
Okay.
if it was 35 for 1, then I'll get 70. Or is it 35.5?
It's 35.5, yeah. So you get 71, yeah.
Miss, so why couldn't
Oh,
just apply?
35. You don't care.
What was that?
I was just asking like why couldn't it be like 35 since 35.45 if it could just be 35, or that would be wrong.
Oh, that's what it said. Oh, what I think so. It's 35.49, you said?
No, 35.45, miss, but I see people
Oh.
use 35.5, so I'm asking if 35 could work. Or it would be wrong.
It wouldn't be wrong, but it would throw off your answer by a fairly significant amount.
Oh,
Because
the
if you
35 you did I use, miss? But all right.
no man, use 35.5 because it's like the isotope thing that we're talking about when we just started, or we're saying that when you do the weighted average, it would be 35.5. Like when you do the weighted average, you do the percentage by mass of chlorine 37 with chlorine 35, it would end up there in the middle, 35.5. So always use 35.5. That's what they determine to be the average. What do we call it? Relative atomic mass. Okay?
Okay.
So you use 35.5, so that means that 1 mole is 71 grams. So 0.05 moles is how many grams?
3.55.
Exactly, 3.55. And trust me, I'm Jabari or Jamar, I don't know who said that, but it makes a big difference if you were to say 3.5 grams versus 3 if you were to say 3.5 grams versus 3.55 grams, that's very different. Like that's how much is that? That's like it's different because remember when we were talking about how we were doing like limiting reagent versus excess reagent stuff, and like if you were off by 0.1, it would make a difference in how the reaction proceed. You have to be specific, like down to the significant figures, and so that's why you have to keep this. So it's 71. So use 35.5, you're gonna get 71, and you get 3.55, and just leave it at that. Okay?
Yes, miss.
Okay. So we are at the end, and we're able to get through one question, and I have a ton of other questions for you. So I have 2 propositions to make right now because I really wanted to get through some more questions with you guys, but I wasn't able to. But first of all, I want to make sure this is more, it's a lot to grasp, but I want to make sure that what we did cover today was more or less clear to you. So let me know if it was clear today. And then the next thing that I want to get from you guys is, but I guess 2 things. I want us to have to do more problems together as far as this goes before the past paper stuff. So what I'm saying is, if there's interest and you want to have a live more problem solving session for electrochemistry, I could schedule something for maybe early next week, maybe like Wednesday or Thursday of next week. We do something like this where we're just doing the problems, or I can just send you problems to work out on your own, and then you let me know if you have any problems with them. So here it is. So there are 3 things. How was this today? Was it clear more or less? First things first, answer that. answer that for me right now. Was this clear what we did today? Or
Yes.
how we ended today? Was this more or less clear?
Yes, miss, it was clear.
Okay. So then now, can I hear from some others as well? I think that was Elizabeth. Thank you for that, Elizabeth. Can I hear from some others if this was clear? And then I'll go to the next layers of question I have for you guys.
It's clear.
That's clear, miss.
Miss,
Okay.
to some extent for me.
Okay, yeah, the Faraday thing can be a little bit tricky. And in our next session, I'll try to make it a little bit more like this is this, right? But I think I went back and clarified it today. But the next session that I hope to have with you, I hope to clarify it even a little bit more so you can see it more clearly why we have to do the one Faraday and the one this and the one why it's one is because of the singly charged versus doubly charged versus triply charged. And I want to make that clear to you guys, and we can do some example questions that would make that clearer, right? And I want to, like, I would very much rather be guiding you through the questions and have you do them on your own. But if you want to do them on your own, that's fine. So what day would work best for you guys for a makeup session? Maybe we'll only do an hour, right?
Miss,
Of just solving it.
Good.
Who is that talking now?
Elizabeth, Wednesday sounds good, miss.
Okay, Wednesday.
Agreed.
Wednesday. Let me check my calendar. So we could do Wednesday and then so just to wrap up. So that would just wrap up all of this stuff. And then now what I want to talk to you guys about was the past paper marathon, right? Which is more involved, and I'll have like extra supplemental material that you get as a part of your package. So what I was thinking of is that we would start doing those marathon sessions because the exam is, I always mess up the CAPE date and the CXC date. I think the CXC
May 18. May 18.
Okay, May 18 is CXC. So then, all right, so then we have time. All right, so maybe then we can start on that weekend. So the 16th.
Oh yeah, and the multiple choice is June the 3rd.
It's June the 3rd. Yeah, so we have time then. So if we can start the past paper marathons on the weekend of the 16th. Yeah. So April 16th, that's Saturday. And we could do.
No, I work on a Saturday, no. Well, for me, no.
So I'm saying, would it be better to do it on a Saturday or a Sunday? So Sunday, what time?
Well, any time on Sunday for me, but Saturday I work at a harder, so that's impossible for me on Saturdays.
Okay, so let's say Sunday. Let's do it like this. I know that this time works for you guys already from this. So let's say we would do from 1. So I was planning on doing like 4 hours. So I don't like wear you guys out, and we can take like a 15-minute break in that for you to get something to eat or some water and then come back. So then it would be Sunday. So that would be like a 1 to 5. Sunday 1 to 5. And then so that would be the 17th. And then you guys can let me know if you want to do it every Sunday up until the exam. So that would be what? That would be 17, 24, 1st of May, 8th of May. Or
a good idea to do it every Sunday until exam, because at least we'll get more practice and can go through more papers.
Okay. All right. So then so that would be, if we start on the 17th, it would be 17, 24, 1st, 8th. And then the Sunday before the exam, it's just you in your brain. I'm not going to talk to you that Sunday before the exam, right? It's just you and yourself getting things clear. So it will be the 17th, the 17th of April, 24th of April, 1st of May, and 8th of May that we would do the past year marathons, 1 to 5 every Sunday. And the rate that I came up with is 1,500 per session. What do you guys think of that? So that would be over the duration of it, it would be per week per session. So 15 times 4. Somebody do a quick math for me. That's what the entire thing would cost then, right? So 15
6,000.
So it would be 6 for the entire session, for the 4 weeks. So $1,500 a day. If I have any Trinidadian students on here, it would be 66 TT per session. I think that's right. Yeah, 66 TT per session. And then, so every week, 1,500, 1,500, 1,500. And then, yeah, so that's what it would be. And so what I'm saying is it's 1 to 5, it's 4 hours of you and I non-stop problem, past paper. And I'm going to give you some supplemental information as well. And of course, like little tips and tricks and little coaching things throughout, you know, just general exam readiness exam tips, right? So it's not, yeah, so it's what I'm saying is a package. It's not just like, oh, me just got me a PM is $1,500 to do the problem them. See, it's like a package deal. So what do you guys think of that? Let me know. Drop it in the chat, talk to me and let me know what you guys think about that. I'm gonna like stop live streaming on YouTube here. But if anybody's on YouTube, I don't want to like talk